All right, good morning. Try again. Good morning.
Morning.
Well, I know I got a ton of energy now. All right. So before we get started with the lesson today, just some things that you want to remember about this week. So we got a test coming up on Wednesday or Thursday, whichever one is for you. And the test is going to cover curved linear motion that we talked about last week, momentum and impulse, which we discussed last week, plus the lesson we're going to get today, which covers a lot of the same stuff we discussed last week. And then conservation of momentum. Conservation of momentum is going to be what we're talking about next. So when I see you guys tomorrow, we go over conservation of momentum, boom, you have your test in the next class. Now, the test is going to have multiple choice as well as problems. The problems on the test are going to be very familiar to you because they're going to look a lot like these here, okay, which are 13 of them. And after today's lesson, you should be able to do 9 through 11. So 1 through 8 should have already been done. 9 through 11, you should be able to do based on what we talk about today. Okay? Do you guys have any questions about any of that? Nope? Okay. All right, so today's lesson, like I told you, covers a lot of the same stuff that we started talking about after the curvilinear motion lesson last week. So this will be familiar to you a lot. But what I want to do is I kind of want to start where we left off. If you recall, last time we were talking about momentum, what it was, and impulse, right? Okay. And we discussed the idea that when you impart an impulse on something, which we know is a force applied over a period of time, for a period of time, right? When you apply an impulse on something, what happens? Raise your hand. What happens when you apply an impulse on something? When you think of the person that I applied the impulse on, I think it was Colton, right? What happens? Yeah. Huh? It moved. Okay. And it doesn't have to be at rest. I can impart an impulse on something that's already moving. And it's going to move differently. So what specifically happened in that movement? Yeah. The velocity of that person or that object changed, didn't it? If the velocity changes, what is an impulse changing overall? It's what?
It's changing the momentum.
It's changing the momentum. So remember, we said that impulse creates a change in momentum. So if you want the momentum of something to change, you imparted a force on that object for a period of time, and you'll change its momentum. Now remember what momentum is. Momentum is two variables, right? It's mass and velocity, right? It's mass times velocity. Well, when I imparted an impulse on Colby, so I imparted an impulse on Colby, I didn't change her mass. So out of those two variables for momentum, what's changing? The velocity, right? Okay. Now, are we good with that? Do you have any questions about how impulse changes momentum? We're good with that? Okay. Now, let's say that I have a 0.05 kilogram egg. Let's take an actual egg. So I have a 0.05 kilogram egg. Right here. Okay? Now, let's say that I throw this egg. Let's say I throw this egg at around 50 miles an hour, okay, which is around 22 meters per second. So I want to throw it so that I have a 50 mile an hour egg going at that wall, okay? Now let's say I want to change the momentum of this egg to 0. So I want to throw this egg and I want to change its momentum because it's going to be going 50 miles an hour, but I want to, and so we know that, first off, let's calculate its momentum right there before we even do anything. If it's going 50 miles an hour, velocity is 50 miles an hour, which is 22 meters per second. And we said the mass of the egg was 0.05 kilograms. What is its momentum right now if I throw it at that velocity? Real quick. Come on, you're just multiplying two numbers. What's the momentum going to be? The initial momentum. What's it going to be? Huh? 1.1 kilograms meters per second. All right, 1.1 kilograms meters per second. Now, let's say I want its momentum to go to 0. So I want it to go from 1.1 to 0. Is that a momentum change? Is that a momentum change? Okay. What creates a change in momentum? We just said it. Yeah, well, that's what's happening. But what creates a change in momentum? Impulse. So I want to impart an impulse on this egg to make it go from its original momentum of 1.1 kilogram meter per second to 0. So how do I do that? How do I get its momentum to change from 1.1 to 0? What can I do? Yeah, well, specifically, what am I going to do? Throw it at the wall. Right? If I throw this egg at the wall, it should go from 1.1 kilograms meters per second, which is the momentum it has when it leaves my hand, because it's going to go 22 meters per second, and it's 0.05 kilograms, to 0. Would the wall impart an impulse on the egg? Over the years, I've done this many times, and it got really messy. So I've learned to put it in a Ziploc bag. Yeah, I know. You wanted to see mess, right? So, okay. There it is. Woo, still messy. Okay. All right. Now. Okay. So here's my question. Let's talk about the impulse this wall just put on the egg. All right? Did it apply a force on the egg? Did that force, was that force applied over a period of time? Yes. Now let me ask you this. Which of those two variables, F or T, was very small? T. T was very tiny. Okay? T was very tiny. Erase this. Right. T was tiny. Remember, the wall created an impulse on the egg. The time the wall imparted its force on the egg was small, wasn't it? You probably couldn't even count that fast. It was less than a second. What about the force of the wall on the egg? Was that small or big? It was huge. Now remember what impulse is, force times time, right? So the impulse the wall had on the egg was a large force in a tiny little bit of time, right? And remember, the impulse was the same as the change in the momentum of the egg, which was 1.1, right? Because it went from 1.1 to 0. The change is 1.1. Does that make sense? We good on that? Okay. Remember, whenever an impulse is imparted on something and the something breaks, it's not the impulse that breaks it, it's the force that breaks it. Okay? Not J, it's F. That's what breaks it. The force of the walls were broken. So here's my question to you. Let's say I have another egg. And I want to do the same thing. I want to throw this egg 50 miles an hour. Okay? So it's going to have the same momentum that it started with last time when it leaves my hand. And I want it to have the same change in momentum. I want it to go from 1.1 kilograms meters per second to 0. I want to have the exact same change, but I don't want to break the egg. I want to have the exact same change. I want it to go from 1.1 to 0, but I don't want to break the egg. tell your partner right now, if I don't want to break the egg, what has to change to give me the same change in momentum but not break the egg? How can I do that? Talk to your partner right now. Gotta have the same J, but it doesn't break. Anybody got an answer? 1, 2, 3, 4. There's a lot of talking for just 4 or 5 people. Okay? Who wants to give it a shot? All right? I want to make the time longer, so the time bigger. So if T gets bigger and J's got to be the same, then F would have to get what? And if F, remember, since we said F is what breaks the egg, if we make F smaller, the egg what? Shouldn't break. So if F gets smaller, then we have to make the time of contact bigger. Does that make sense? How do I do that? Well, it's still going to hit the wall. No, this is not the time. This is not the time that the egg is in the air. This is the time of contact. This is the time that the force is applied to it. Right? So when the egg's in the air, no force is being applied to it yet, other than just the air. Right? This is the this is the force of the contact. This is the time of that same contact. So we're still talking about the egg hitting something. Your idea was right though. We want a small f on the egg, which means we're gonna have a big T. Yeah.
Throw it at like a cushion.
Throw it at what?
At like something soft.
Throw it at something soft, like a cushion. Now what would that do?
Increase time.
Why?
It's gonna like sink into it.
So it would take longer to sink into a cushion, so time gets bigger, F gets smaller. Does the egg still get to 0?
Yes.
Because eventually it stops. It just takes longer to stop, but it's still, so I still have the same change in momentum, right? So throw it in a cushion. Does that make sense to everybody? Yes or no? Okay. Well, I don't have a cushion. 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 Oh, but I have a bed sheet. Thank you for noticing. I have a bed sheet.
It rolls down.
So we're going to try that. Actually, somebody's going to throw and try it. So I need 2 people to come up and hold this sheet up. Come on. Come on. You hold that in. You come over here and hold this in. Now, we're going to do this. Hold it up high. Now, at the same time, hold this end up. Hey, hold this end up. So it creates a lip. This has got to go high though, and it's got to get away from the wall. Y'all got to be like almost up to this. All right. This way, when the egg hits, it's not going to fall and hit the ground. Does that make sense?
Yes.
Okay. It's got to be high. Who wants to throw it? Who can throw? Okay, come here. Yeah, I've had that same answer before. And it goes everywhere. It's all right. For some reason, when it's an egg, people get really cautious. It's horrible. I don't know if I would be here. I cannot vouch for her aim. No, you don't have to. You should not have to. Hold, but here's the deal. You got to hold it straight up. Honestly, I don't know what kind of aim Joy has. We're going to try it with just a raw egg, not a baggie. Okay? So she's got to hit. You got to hit her right in there. Now I'll give you a practice run. Now that I'm thinking about it. Give me that test. Pull that string out. Okay. We'll give you a practice run with a tennis ball. All right. Hold the sheet up. Hold the sheet up. Yeah. But it's got to be in the middle. Well, whatever you can do to get it in the middle of the sheet. Oh my gosh, yes. Go ahead. All right, go ahead. That's what I'm saying. Y'all see that, right? Right? That's why we take a practice. Where's the ball? Oh my gosh. All right, hold on. We'll let Gina do it. Hold it up. You gotta hold that left side go. There you go. All right. Oh, we're taking our sweater off? We're like down to business now, huh? Okay. Oh Lord, hold on. Look, we wanted to hit here so that in here so that it's caught by the lip. The lip can be small. The lip can be small. The lip can be small. But this is got to be. All right.
Calling your Chanel Mrs. Gives you running basketball practice? No.
All right, Chanela.
You got it right there? Yeah.
Chanello.
Yay! What's funny is, give me the ball.
She's not even my clothes.
Let's try one more time with this, just to be absolutely sure.
Okay. You got it.
That could have been a fluke. Lip. All right.
Lip.
I'm telling them to lip. Don't worry about it. Throw. Okay. All right. Okay. All right, now we're doing the real thing. Real thing! All right. Are you ready? There we go! All right. All right, back here, have a seat. Oh my Lord, that was so stressful. And it shouldn't have been that stressful. Oh, wait. Go ahead, Gina. Man, go with this. All right. So now, the egg, it had a momentum of 0 when it hit the sheet, right? It stopped. It stopped. So we had the exact same J. The difference, though, was J was the same. That didn't change. But we had a small f and a very big T. Okay? Same change in momentum. Same change, 1.1 kilogram meter per second. But remember, it's the F that breaks the egg. So we were able to save the egg, creating the same result, but with two variables that changed within that. Okay? Any questions? This is exactly the purpose of an airbag. All right, we talked about airbags. Remember that? If you're in a car going 60 miles an hour and you hit a wall and you stop to 0, obviously, your head does the same thing, right? It goes from 60 to 0. Well, it's either going to do it against the steering wheel, where it's going to be a big F and a little T, right? Where you're still going to go from 60 to 0, you're still going to have the same momentum change, or it's going to do it into an airbag, which is like the sheet, where it's going to be a little F and a bigger T. Your head's still going to come to rest. So that's the point of an airbag. All right, good. So now let's take a look at some things that we probably already have discussed. They should make a lot more sense. So we know that momentum is basically the difficulty in stopping an object, right? It's the amount of movement something has. So if it's not moving, it doesn't have momentum. It doesn't have inertia. Yes. Don't confuse momentum with inertia. Okay? Impulse is force applied to something for a period of time. Okay? And we learned how that force changes the motion of an object depends upon both the size of the force and how long the time the force is on the object. We saw that with the egg. When it was a big F and a little t, the egg breaks. When it's a little F and a big T, the egg is not broken. Okay? Whenever you create an impulse on something, you create a change in the momentum. We learned that last week too. This is all review. Right? The object will either go faster or slower. It depends, and its mass won't change when you hit it. Because you're not changing mass, you're changing velocity of momentum, right? But notice it says it will go faster or slower. In this case, the egg went slower, right? Stop. But you could also push something in a direction where it was either at rest and you made it speed up by hitting like I did with Colby, right? Or it could already be moving and you come behind it and push it in the direction it's going currently and it'll move faster. Does that make sense? So you can speed up objects too with impulse, okay? Therefore, impulse causes a change in momentum. So all of this makes sense. Now notice what I have right here. We know that change in momentum is mass times change in velocity because your mass isn't changing. Okay, when momentum changes, it's usually the velocity that's changing. And that would just simply mean the final velocity minus the initial velocity. Make sense? Okay. A bowling ball and a tennis ball can have the same momentum, even though they have different masses. Because remember, momentum is mass times velocity, right? So a bowling ball, which has a huge mass, okay, is going to be moving at some velocity. If we want a tennis ball to have the exact same momentum, but it has a very tiny mass, right? A tennis ball's not as big as a bowling ball, right? It would have to have what kind of a velocity? No. Tennis ball. It would have to have a huge velocity, right? Right? To equal the momentum of a bowling ball that has a small velocity. Okay? Here you got a ball that's 7 kilograms, moving 2 meters per second, momentum of 14. There you have a tennis ball, which is way smaller, 0.07 kilograms. It would have to go 200 meters per second to have the exact same momentum. Make sense? Okay? We know that impulse changes momentum. We've seen that with all these examples. So greater impulse exerted on an object or greater change in the momentum of the object. The impulse can be exerted on an object to either increase or decrease the momentum. Now this is when contact sports come into play. Okay? So let's take a look. Increasing momentum, hitting a golf ball. Okay? If you were going to swing your club and hit a golf ball, all right? So let's say we have a ball here, club head is coming and moving towards the right. The rightward moving club head is going to experience a leftward force of the ball on the club. The golf ball is going to experience a rightward force, the club on the ball. The forces have equal magnitude in opposite direction. Okay? Look how the ball squishes in. They took this picture right as the club hits the ball. You see how the ball squishes in a little bit? They all do that, right? So you've got this force that's pushing the ball in, okay, over a period of time. Now, if you're trying to hit this golf ball really far, do you want it to have a greater change in momentum or less change in momentum? Greater change. So you need to apply a force on it over a longer period of time, right? To give it a greater change in momentum. Does that make sense? So when you hit the golf ball, you don't want to just boom, hit it like that. You don't want to just hit it. You want to hit it and follow through, don't you? Right? Baseball and the bat, same principle. Look at the ball. Look how it performs when it hits the bat. Again, they took a quick picture right when the ball and the bat hit. The impulse of the bat decelerates the ball when the ball comes at it, right? So the ball's going to slow down, right? And then the bat's going to accelerate it in the opposite direction very quickly. The longer the bat is in contact, the greater the change in momentum of the ball, right? If you're increasing the amount of time that force is being applied, you're going to increase the impulse on the ball. You increase the impulse of the ball, you're going to increase the change in momentum of the ball, which means the ball's going to go farther. So again, that's why we follow through. Okay? All right. Decreasing momentum. If you look at this, it says, it takes an impulse to change momentum. Remember, impulse is F times D. If you want to stop something's motion, decrease the momentum, you can apply a little force over a longer time. All right, look here. Here you got a truck with a huge momentum coming into a haystack. The truck's going to hit the haystack and eventually come to rest. Well, the haystack is going to apply a small little force on the truck, right? But over a longer period of time. The truck has to literally travel through the haystack over a longer period of time to stop. So this represents a little force over a longer time. Or you can apply a lot of force over a short time which is what happens when it hits a wall. In both cases, you have the same change in momentum, don't you? You go from some velocity to 0, and the mass of the truck never changed. Yeah. Time starts once contact's made, and it ends once the momentum has completely changed. The time is the time of contact. So the time stops when the contact is finished. That's what I should have said. It starts when contact is initially made, and it stops when contact is done. That's a different motion. It's when it stopped hitting horizontally, then it became something different. Now remember, it's the force that breaks things, not the impulse. Okay? Such as what we saw with the wall and the egg. And if you can make the force small enough, it won't break it. Now this is all stuff we kind of already talked about. I'll let you read this later. I want to get to this pole vault thing. Right down here. Anybody in here pole vault? Tried it? Y'all know what it is, right? Yeah, that's the one where they got the big long pole, right? And they run, stick it in the ground, fly over a bar, right? Whoever came up with that said, hey, let's try this for a sport. When the pole vaulter lands, what does he land, or she land on? Yeah, well, back in the day, they didn't have mats. Back in the, way back in the day, they landed in head. But yeah, we have mats. Now, if there was no mat, when the pole vaulter hits the ground, will her momentum change? Yes, of course. She has some velocity times her mass right before she hits the ground, and then she has another velocity times her mass once she hits the ground. Okay? What if she hits a mat? If she hits a mat, does she have the same change in momentum? Yes, because she still goes from some velocity to 0. Well, what's different? No, the impulse is the same. Remember, it's the same change in momentum. Right? If she hits the ground or hits the mat, the J is still the same in both cases. J is the same. The difference is F and T. Right? When she hits a mat, the F becomes smaller and the T becomes bigger, doesn't it? Remember, it's force that breaks the A, right? So it's force that would break the person. So you're trying to decrease the F and still have the same change in momentum because they eventually are going to stop anyway. So you got to have a longer T. So that's why we use a mat, right? That's your cushion. That's like the egg in a sheep. Okay? Any questions on that? Okay. Decreasing momentum over a short time versus a long time. I don't know why any boxer would do this, but if the boxer, so let's say, you're boxing, right? And another boxer hits a boxer in the face with the punch. The boxer who gets hit, okay, it's going to be an impulse, right? Force over a period of time. If the boxer moves their head away from the punch, okay, then they're extending the time of the punch, right? Which is decreasing the F. So they don't get hurt as much. So boxers are all trained to absorb punches. Like if it's a body blow, they absorb it like this. They don't just do that, they absorb it. Because they're trying to increase T and decrease F. Same impulse though. The fist is still going to go to 0. Okay? But I don't get this way. If the boxer were to move towards the punch, then you're decreasing the time of the hit, you're increasing the F. You're still getting the same impulse. It's going to hurt more. That's somebody who shouldn't be boxing. Right? Airbags, we already talked about that. Airbags extend the time over which the impulse is exerted and therefore decrease the force. Right? Just like the sheepy egg. And you've all seen, people that karate chop bricks and boards. You've always wondered how they do that. Well, it has to do with impulse. When they put their hand down and they're chopping these boards, if you do it quickly, right, the time is small, the F is long, the force is huge. So you're increasing the force by doing that. They should all break. Okay, here's our problem. Let's try to solve this problem. Now, before we solve it, hold on. You got to remember some vector math. Remember when we did vector analysis? Okay. Velocity. You remember we had acceleration, we learned about acceleration, we learned about velocity, right? But you remember when we put a negative sign in front of acceleration, what does that mean? It's decelerating. Well, what did it mean when we put a negative sign in front of velocity? It's what? It's going in the opposite direction. Okay? Now in this problem, a soccer ball that has this mass is coming straight at, and let's say it's you, a 75-kilogram soccer player. You're the soccer player. So this ball is coming towards you. Now, you're going to kick it. The ball's coming at you at 13 meters per second. Your foot's going to go in the opposite direction, right? On the ball. And you're going to kick it. When you kick it, the ball's now going to go that way at 22 meters per second. You see that? Everybody read? You got to read the problem. You got to understand what's happening when you read the problem to be able to solve it. So the ball was going initially 13 meters per second in this direction. Finally, it's going 22 meters per second in that direction. With an average force of 1,200 newtons. That was the force of your foot on the ball. Look at the question. How long are his foot and the ball in contact? So ladies, we're trying to find time. The only formula we've discussed in this unit that has time in it is impulse. Right? That's what's going to help us get time, is the formula for impulse. We also know that impulse is related to change in momentum, right? If I go back to this formula here, right here, Ft equals this, doesn't it? Y'all see this? Ft equals this. Do we have a change in velocity in our problem? Yeah, we have a soccer ball that was going 13 meters per second that way, now it's going 22 meters per second that way. We do have a change in velocity. We're trying to find this t. Right? Alright, so let's go back to the problem. I want you to try to solve it. Okay. See if you can't solve how long the ball and the foot are in contact.
The kicking at 22 meters per second.
That's now how fast the ball is moving in the other direction because of your foot force.
It's not his.
No. Well, yeah, this is direction.
22.
No. It's 13, then you kick it, 13 meters per second, then you kick it, and now it's 22 meters per second. The ball, huh? You what?
I don't read it that way. I read 13, 22.
Right. The ball's coming at you at 13 meters per second. You kick it in the exact opposite direction at 22 meters, so now it's going 22 meters per second in the opposite direction.
I read it as 22 minus 13 in the new direction.
Okay, but you're not, you gotta treat velocity as a vector. You gotta treat it as a vector. I'll explain that in a second to you. Just for right now, treat it as a vector. Knowing what you do to velocity when it goes in the opposite direction compared to an original velocity. Yeah. Good job. this is the velocity at the end, right? So we'll just keep it at 22. But how is this velocity compared to that? Okay, so it's VF minus. There you go. This is right, but remember this velocity is in the negative direction of this one. So it'd be this minus this minus. No, this is in the opposite direction of this. This minus. What do you do to V when it's in the opposite direction? What do you do to V when it's in the opposite direction? Yes, so it'd be this minus what? It's in there. It's in the problem. Yeah, because we're all talking about the ball. It's VF, minus VI now. So we put 22 here. And VI is in the opposite direction of 22. So it should be VF minus VF minus, yeah. Okay. No. So this would be, make that positive. So we're gonna make this positive, and this is the opposite direction. This would be this minus one. No. 13 is in the opposite direction, right?
Oh.
So this minus. We still accomplish one being the opposite direction of the other. We just do it in such a way we don't get a negative time. All right, so let's take a look. Here's the thing you have to understand. We know that momentum, change in momentum, is mass times VF minus VI. VF is 22, right? Isn't that the final velocity of the ball, 22? VI is 13, right? But in VI opposite 22? So it should be 22 minus negative 13, which it becomes 22 plus 13. So when you do that, right here, this is what is causing the problem for all of you. VF minus VI, that's correct. So it's 22 minus negative 13. The reason it's negative 13 is because 13 is in the opposite direction. And that equals F times T. I'm sorry, that equals 1.3 times 35. So you set that up equal to FT, and you solve for T. And you get a T value of 0.0379 seconds. Okay, again, if you look, you're basically saying F times T is equal to that, M times VF minus VI. And you're solving for this. You know F, you know M, you know VF, and you know VI. You know all those. But you remember, it's going to be VF minus negative VI, because in this case, VI is in the opposite direction of VF. Let me ask you this. Let's say you want to kick a soccer ball really far. Okay? So you have two choices. It can either be at rest, and you run up and kick it. Now, if it's at rest and you run up and kick it, what is its initial velocity? Okay? And then whatever you kick it with, that's the final velocity, right? So let's just say I kick it with a velocity of 60 miles an hour. Okay? So the change in velocity would be 60, wouldn't it? Right? Right? Change would be 60. And so it'd be 60 times whatever the mass of the ball is. That would be the change in momentum of the ball. Okay? But what if I have somebody roll it at me? If I have somebody roll it at me and I kick it, and it's rolling at me at, I don't know, 5 miles an hour. Right? Now its initial velocity isn't 0. It's now 5, right? But it's negative 5. And I still kick it with 60. So would it be now 60 minus negative 5? Which is 65. That's a greater change. Which means the ball is going to go farther. So anytime you're trying to kick a soccer ball far, you want somebody to roll it at you rather than just set it down on the ground and kick it. It'll go farther if somebody rolls it at you. Which is why a lot of times they'll roll the ball at the goalie and the goalie will kick it as it's being rolled at him. Okay? It'll go farther. Okay? Or if you roll it out in front of you in the direction you're going to kick it, that would even be less than 60. That'd be the worst way to kick it far. Okay? So see, there's a lot of physics involved in a lot of sports. So let me put this up here. Okay. So during this contact time, which is 0.0379 seconds, which is just under 40 milliseconds, the ball compresses substantially and then decompresses. This happens too quickly for you to see. This compression occurs in many cases, such as hitting a baseball, a golf ball. We already looked at that. This is how you get a greater change in momentum when you kick a ball coming at you with a force versus kicking it at rest. Okay? All right. Any final questions? Yeah. So, I know that F, so here, do you recognize this formula right here? Okay, so wouldn't T be equal to M times VF minus VI over F? Right? And this right here is this, which is 45.5 divided by the F, which is 1200 newtons. That's just an algebra question you were asking me. It had nothing to do with physics. Yeah. Yeah. Well, nothing's being squared. Okay, so let's look at that. That's a good question. So up at the top, I have. Can I erase this up here? Okay, I'm just going to put this math up here for you. So we have 45.5 kilograms meters per second, right? That's in my numerator. And I'm dividing that by 1200 newtons, right? Remember what a newton is. A newton is a kilogram meter per second squared. Right? Now let's look at these two units. I've got this divided by this, right? So kilograms times meters per second, that's this one. I want to multiply it by the reciprocal of my denominator, all right? Well, the reciprocal of this, if you flip it, will be seconds squared over kilograms times meters. That cancels that. That cancels that. I'm left with seconds. Does that make sense? Okay. Guys, try to do 9 through 11. You got 12 minutes. Plenty of time. Get started right now. Don't waste time talking. So, you see this right here? That's how I got it. 1.3 times 35.